Good afternoon. Welcome to the Past Less Traveled, Abusing Kubernetes Default in Mandalay Bay, Lagoon Room JKL with Ian Coldwater and Duffy Cooley. Before we begin, I have a few brief notes. Stop by the business hall located in Mandalay Bay, Oceanside and Shoreline ballrooms on level 2 during the day and for the welcome reception at 5:30 p.m. The Black Hat Arsenal is in the business hall on level 2, and join us for the Pony Awards in Lagoon JKL at 6:30 p.m. It's in this room. Thank you for putting your phones on vibrate as well. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick it up. Ian, Duffy, it's all yours.
Thank you.
Thank you.
Everybody hear me okay? Awesome. Before we started, I wanted to just thank all Black Hat and all of the organizers and all of the review board, the people who put in the work for all of us to be here today. That's awesome. And thank all of you for being here and taking time out of your day to be here with us. My name is Ian Coldwater, and this talk is called The Path Less Traveled, Abusing Kubernetes Defaults. If you are here to hear about something other than Kubernetes, you're in the wrong room, and that's all right. We can hang out anyway. I'm a lead platform security engineer at Heroku, and I specialize in hacking and hardening Kubernetes, containers, and cloud infrastructure. Before that, I was an independent penetration testing consultant focusing on the same.
My name is Duffy Cooley. I'm a staff cloud native architect at VMware, and I focus on helping enterprises find success with VMware in this kind of new cloud native regime. I'm a part of a weekly video blog that's called TGIK. You can find it online at tgik.io. And if you're interested in the Kubernetes space, I highly recommend that you review what's there.
We're really excited to be here talking with you today. So the first thing we want to say is check your assumptions. If you have assumed that Kubernetes is secure by default, or that applications deployed on Kubernetes are secure by default, we recommend that you don't, because they aren't. When Kubernetes gets left on out of the box, you can do all kinds of wild things with it, which is what we're going to show you today. But before that, let's talk about Kubernetes defaults, because it's a little bit of a misnomer. Like, the cake is a lie here. There is no singular set of Kubernetes defaults. It varies widely depending on public clouds, distributions, just out of the box, and every single cluster is probably going to be a little bit different according to how it gets configured. So that attack surface doesn't always look the same, but generally speaking, we can speak to Kubernetes as a system, how it works, and how to attack that. So that's what we're going to do.
So I work on a project called KubeADM, which is actually trying to rationalize some of those defaults and provide reasonable defaults for bringing you to the place where you have infrastructure, where machines and networks already stood up, and you're trying to get to a fully configured Kubernetes cluster. KubeADM does actually provide a reasonable set of default security options, and we're probably going to talk through a little bit of that, but all of the demonstration environments that we're going to be showing off today in this talk are actually brought up using a project called KIND, which stands for Kubernetes and Docker, and it leverages KubeADM to stand up the cluster. So in our resources slides, you can find a lot more information about what we're doing here.
It's worth noting that we're attacking this cluster that has been set up with the same reasonable and relatively secure set of defaults. Actual defaults that are not defined by KubeADM are usually worse. So keep that in mind. So what is Kubernetes?
So Kubernetes is a container orchestration system. And it describes a class of system that helps us manage the lifecycle and the complex architectures of some of these new cloud native applications. As a cloud or as a container orchestrator, it's actually pretty successful. Most people who are actually looking at Kubernetes are looking for two things. The first is actually a better efficiency through like API models, so you can actually deploy some of these complex applications and figure out how they will connect and secure them and that sort of stuff through a single API. And the second is actually bin packing, or better efficiency of those machines that they deploy in some of the more expensive clouds that we see out there.
When we're talking about Kubernetes as an attack surface, Kubernetes really means two things. It means it's an application with its associated set of binaries that can be, and the application can be configured. And it's also an API-based platform defined by YAML. So both of those things can be attacked in different ways, and we're going to cover them both. So how does Kubernetes work? Let's talk about what's in there and how those parts move.
So in this diagram, you can actually see all of the actual parts that make up the application that is Kubernetes, right? In the left-hand side box, you see etcd, and etcd represents a key value store where all of the state for the cluster is kept. This is where we would hold things like config maps or configuration files that will be associated with pods when they're brought up. In the middle, just to the left of the etcd pod or etcd image, we have the API server. And you can see by the plethora of arrows that everything talks to the API server. The people on the outside, the services on the inside, everything talks to that API server. And that the API server is the only thing that talks to etcd. The API server does kind of what you would expect an API server to do. It's going to handle authentication and authorization. It's going to take care of validating all of the manifests or objects that get submitted to the API, and it's going to handle that sort of stuff. If we look below the API server, we see the controller manager and the scheduler. And the scheduler does kind of what you would expect it to do. Its job is literally to associate a pod or a pod manifest, and we're going to get more into like what that is and see some examples, with a specific node or kubelet. And the controller manager is a bit more complex. The controller manager's responsibility is actually to run a number of different control loops that are each responsible for breaking down the higher level of abstractions inside of Kubernetes down to the lower level ones. So if you've played with Kubernetes at all, you would have made a deployment. The controller manager is responsible for turning that into pods. On the right, we see two kubelets or two worker nodes. And the worker node is running that agent, the kubelet. And that kubelet is responsible for keeping track of all of the work associated with that particular node and starting up and managing the lifecycle of containers directly. So the kubelet, when it pulls down a manifest, it's actually going to interact with Docker to create those containers that make up that workload.
As an attacker, let's take another look at this series of Kubernetes components, because we're going to be talking a lot about how Kubernetes works today, because it's really important to be able to understand how it works on a deep system level, to be able to understand how to attack it well. So etcd, we have this key value store that contains all of the state and all of the information about what's happening in the cluster. As an attacker, etcd is a high value target because it contains interesting information that I might want to exfiltrate or steal, such as cloud metadata and credentials, things like that, potentially. It also is worth noting that etcd, because Kubernetes is a loosely coupled distributed system, etcd is writable. It's not just read-only, it works both ways. And so because etcd is the final word on like what is happening, the state in the cluster, you can write to it, and then you can modify state, which can give you all kinds of options as an attacker. The API server is the highest value target as an attacker because the API server, as you can see, either touches everything or everything touches it. If you can get control over the API server, which is what's going to dictate what is allowed to be, what kind of traffic is allowed, what's happening, is going to be like making the orders for what's going on there, then you can get access to pretty much all of the components, and you're able to get a fair amount of control, like a lot of it, over the cluster. So going over to the worker nodes, the kubelet is incredibly valuable as an exploit target because the kubelet is what executes all of the decisions that are being made with your configuration and is able to control the state of the cluster and what's in it. The kubelet has its own separate API that interacts with the API server. If you can get access to the kubelet, you can do things like create users, you can create service account roles, and you can change around authorization stuff so that you can get that. You can also affect what's in the cluster and get a lot of administrative access if you can get access to the kubelet. The kubelet historically is the subject of a lot of the more high-profile attacks that have happened historically with Kubernetes, like Tesla and ones that have happened over time.
So now we're going to move on to the Kubernetes API part of it. Before we do that, I want to just touch on the fact that there is a lot of configuration in between all of those pieces, securing the communications with TLS and all of that stuff. We don't have time for that in this talk, but suffice to say that diagram is very high level compared to what's actually out there.
There's also a lot of misconfigurations that can happen with all of those components, all of which can be valuable for attackers.
So the Kubernetes API is generally accessed through a number of different means. It's a RESTful API. You can interact with it directly with curl if you want. There is actually a kubekettle is a binary that you can download as part of a distribution of Kubernetes, and that kubekettle binary acts as a local command line tool that you can use to interact with the Kubernetes API directly. And it'll take care of your authorization and authentication using your config.
kubectl is also known as kubectl, kubectl, and kubectl. And when I talk about kubectl, I'm talking about the same thing. And that's important to note because otherwise it's confusing. Think about it like GIF and GIF.
There are some other superpowers that kubectl has. One of the ones I like to tell people about is kubectl explain. kubectl explain enables you to actually explore the entire API. So if you want to know what all of the fields that are defined within a particular pod or deployment manifest are, or what the defaults for those things are, you can use kubectl explain to interact with that API and look at it. Finally, the last command here is basically just showing off kubectl apply, which is how most people interact with it.
As an attacker, if you can socially engineer somebody to kubectl apply your lovely, helpful YAML file that will show them how to use things or whatever it is that you can convince them to do, they run it, they don't look at it, it's yours, and you can do whatever you want with it. So configuration as code can be a pretty powerful thing on all ends. So how do those moving parts fit together? Like what exactly is happening there under the hood?
So we've talked about Kubernetes being a loosely coupled system, and in this diagram, we're going to show kind of like the life cycle of a pod being created. So in the beginning here, we have a person probably making use of kubectl, applying a pod manifest to the API server. The API server is going to introspect that and understand, is this person who's authenticating, do they have a reasonable credential? Do they have authorization to create this resource within the cluster according to the namespace that it's being put in, all that other stuff. It's also going to validate that you have all of the fields necessary to define what a pod is. Once it gets through that entire process, it's actually going to persist that object in the key value store in etcd. And then it's going to report back, pod created, you're done. The API server is now finished with its work. The next part that happens is that the scheduler, who is also watching the API server, gets informed that there is now a new pod, but it is not associated with an underlying node. And so it does its scheduling thing. It just figures out which node it wants to schedule that pod on based on some hints and things inside of the pod spec. And it will actually schedule that on a node and persist basically another field into that pod spec called node name back to that object in the key value store in the API server and then back to etcd. The next thing we have is the kubelet, and this is the one that's actually doing the heavy lifting. I call this out because it's interesting. We think about a pod as two different things. One is a manifest, basically just metadata describing what we want to deploy, and the other is a set of running containers or processes sitting on a node somewhere. So in this case, we're talking about the kubelet pulling down that manifest and setting about the work of creating those containers. It does that by calling out to your container runtime. Could be Docker or Containerd. There are a bunch of them out there. It also will connect to the network and do a lot of the other stuff necessary for the lifecycle of that pod. And it will report back to the API server status. You know, I'm downloading the image, I've started the container, all these things are happening, and it will continue to inform you where it is in that process.
So as an attacker, let's take another look at this moving parts diagram, and let's figure out what's happening there that it could be potentially interesting to us. So the API server, as you can see, does a lot of the kind of moving back and forth here. And the API server is responsible for things like authorization, authentication, and routing. CVE 2018-1002-105, which came out last December, was a server-side request forgery where, no, it wasn't. Oh my God. Okay, what that was attackers could send a specially crafted request and that said connection upgrade. And because they weren't validating for error codes, it just opened a WebSocket, whether or not it was correct. And you could communicate directly with the kubelet and the backend while bypassing the API server's authentication and authorization entirely, which was pretty nasty and pretty easily mitigated, as it turned out, because all you needed to do was validate for error codes. So that's one way historically, if you look at that, how attackers have been able to attack the API server. Another thing that we can do is, you may have noticed that in our components diagram, as an attacker, I didn't actually mention the controller manager or scheduler at all. Mostly because for the most part, it's irrelevant to me, except that you can bypass it by directly scheduling a pod. And if you can directly schedule a pod on a node, you might be able to do some interesting things with it, especially if, for example, your kubelet is scheduled on the same pod as the underlying node, which is the default for kubeadm. So we've had a lot of Kubernetes words here. Anybody want to see how to attack some stuff? Yeah, let's do it. All right, so let's attack thing.
So in this demonstration, we're gonna deploy an etcd client that's pre-configured to access etcd running on a control plane node. Now, as we said, kubeadm puts a kubelet on that control plane node, and so we can use this direct scheduling trick to actually attach to that.
So what we're going to do here is we're going to direct schedule our pod on the underlying node. We're going to dump etcd, get secrets from it, and do some fun stuff.
Yeah. So this is a pod manifest, and it's pretty verbose. It's got a lot of information in it, but basically we're telling it we're going to create a kind pod, and then all of the rest of this represents the body of that post. We're describing the image that we want to use for this. We're just going to use the same etcd image that is actually being used to run etcd inside the cluster, because it actually also has the etcd CLI command line tool. We're providing some environment variables that are actually going to pre-configure etcd for us, so we don't actually have to pass a bunch of command line arguments to etcd CTL. And then we're also going to mount in the certificates that we need to be able to authenticate to etcd using host path, a very powerful capability of Kubernetes.
We'll be talking about that more.
And then we also have host network. And the reason we're doing host network is because we need to basically access that local host address. And so we need to be on the host's network to be able to achieve that. Let's go ahead and deploy that. Now I've used this tool pretty extensively to actually interact with etcd in a troubleshooting fashion. Like if I need to remove a member or understand performance or see what the status of the etcd cluster is directly. But there's other stuff we could do.
So other things we might be able to do, as we said, we could maybe try to see if there's any kind of interesting secrets or credentials in there that might do anything for us. So let's take a look. Well, okay, we've got all of the secrets in there. Those are broken down by namespace. You'll see, kube public, kube system. Kube system, as it sounds like, is the namespace that has system access. Note that there is one particularly interesting one in here called cluster role aggregation controller. Cluster role aggregation controller in Kubernetes by default to this day allows complete administrative access to the cluster to default or by default. So if we can get access to the token, for example, for cluster role aggregation controller, we can authenticate with that token and have complete control over the cluster. So let's do that. Let's grab that token. There's your token. If we use a tool called, this came out in Kubernetes 1.13, kubectl cani auth --list. This was the best thing as a pen tester because before that happened, we would have to manually list out, do every single call to see if we had permissions to do it, which was, as you could perhaps imagine, really annoying and took forever. But Kubernetes made it so much easier for us by just automating our enumeration process for us. So now we can just do that and see all of the permissions that we have on the cluster just like that. So let's try that with this token and see what we got. Oh, we have a wild card. We have access to everything. So we grab that token, we can authenticate with it, it's ours, game over.
You'll find that a lot of Kubernetes clusters are maybe not using TLS between the components, or that you can actually get a hold of if they run kubelet directly on a control plane node, that you have that access to be able to do this stuff.
So some demo takeaways here. Users can create pods that have wild permissions by default. kubeadm schedules the kubelet directly on the underlying node, which you ought not to be, or runs it on that node, which you shouldn't do. And as an attacker, if you can grab that token for that particular role, you can take it over really easily.
And the other two pieces of takeaway here I think that are important is that people frequently think that when you start exploring Kubernetes that being able to isolate nodes with labels or that sort of thing can be thought of as a security boundary. And that's clearly not the case, right? In this case, what we're doing is we're directly scheduling a pod, and that means that the scheduler never sees it. And because of that, you can't assume that the scheduler is ever going to be a security boundary. The last one is that namespace isolation is not enough. If I have access to the underlying host, I have access to that underlying host regardless of what pods associated with what namespaces are in. To mitigate them,
So we mentioned host path, and we're going to go into host path a little farther because host path is wild. Host path is so wild that we named this talk after it. The Kubernetes documentation describes host path as, there is a screenshot that is from that site, a powerful escape hatch. They're not kidding. It is an incredibly powerful escape hatch. You can escape all kinds of things with it. And there's so many options for what you can do if you can volume mount the host and be able to have that kind of control in relation to the host. So we're going to keep exploring that because there's a lot happening here. And we had more exploits here than we had space for. So, use your imagination. Okay, so host path. It mounts a file or directory from the host node's file system into your pod. When I first heard about host path, I was like, what on earth? Like, to me, this is an obvious attack tool, right? Like, what would you even want that for? Does it have like legitimate use cases? And as it turns out, it does.
There are a few use cases. Bootstrapping a cluster, you need host path to be able to get to the stuff necessary to kind of bring the cluster back up in the case of a power outage. Another is Docker and Docker is a common use case. People who want to build containers inside of Kubernetes frequently think that Docker and Docker is a good solution for this. There are other solutions for that out there today, but that's another one of the use cases. You're basically mounting in the Docker socket underneath.
Docker and Docker is very commonly used and also a very good attack target in and of itself, which we'll talk about in a bit. So, Docker and Docker. Docker and Docker, I think that people think sometimes that certain kinds of Docker attacks can only happen if the container is privileged, and that's not actually the case. It is actually possible to, via attacks on Docker and Docker, escalate privileges to root on the underlying host from an entirely unprivileged pod with all of the security things on it. The Docker socket lives at var run docker sock. It's not unique to Docker. Other container runtimes also have them. They'll be differently named. And that is a very valid, great target for us, especially if we can mount it with something like host path. So let's take a look at what we can do.
So we're going to bring up a pod, and we're going to show you the manifest necessary to bring up a pod that has access to the underlying Docker socket. And again, this is a pretty common use case inside of Kubernetes. I find a lot of people doing it, and I shake my head a lot when it happens. But we're going to walk through this manifest because it's a little more complex than the previous one. Up here at the top, we have an annotation that describes the seccomp profile that Docker will use when it's starting up this particular container. Down below, in the security context, inside of the spec of the pod, we are also specifying a user, a group, and an FS group. And this is an interesting detail. This is dynamic. I can change that UID or group ID before actually deploying the pod. If I made this a deployment, I could just edit the deployment and change the UID and GID, and all of these pods would be started up with that new UID and GID. It's not defined inside the container. It's defined at Docker at runtime. And it's basically making use of the user namespace in containerization. We describe the container we want to use, and then we actually use this host path mechanism to mount in the var run Docker socket. We're also making sure that for this specific container, we're not allowing privilege escalation, so no sudo capabilities. We're also dropping all of the Linux capabilities. We're not using any system calls to the Linux kernel that are governed by those capabilities.
Now, as a penetration tester, if I see a context that has all of that security stuff on it, it drops all capabilities. Privilege escalation isn't allowed. It's not running as root, which is relatively rare in Docker. There's a lot happening there, and that probably is going to make my day pretty sad. I'm going to have kind of a hard time, except that with the use of host path, the powerful escape hatch, maybe not. Maybe I'll have a little bit of an easier time. Let's see what'll happen.
So the first thing we're going to do is go ahead and deploy that manifest, and then we're going to be able to see that the UID and GID are exactly what we set in our security context. The second thing we're going to do is attach to that container again and take a look at the definition of the Docker socket. So when you install Docker on a Linux host, generally, in every install that I've ever seen of Docker, it will create a Docker group, and it will associate permissions with that Docker group for the Docker socket. So if you think about it, as long as you have host path, you can actually figure out what group ID that is and just define your pod with that group ID, and you have full access to Docker without running as root. And
to the underlying node.
So people do this because they want to be able to use Docker tools. There are, again, other options out there for that stuff.
It's a very common pattern.
So we're going to go ahead and exec in again and do a Docker run command to create an Nginx instance. And then we can see that in the underlying host. There's our running Nginx instance. And then if we just wanted to drop that from the underlying host, we could actually just do that from that perspective right there.
So, okay, that's all cool as an operator, Nginx, all right, fine. So what can we do with this as an attacker? Well, if you can get If you can mount the Docker socket on the underlying node, as it turns out, a fair amount. When I see this as a pen tester, it's the best thing. It like, you hit the button on the K-Cup maker, you like walk out of the room, you hit enter, your root, you come back, the coffee's done, your day's done. It's instant, it's great. So, hostname, it's ours. And that's it, game over.
So in this example, the host name that I want to show that I'm actually on the machine links. I'm connected to that host right there. And if I touch a file in Etsy, in the Etsy directory, on that host, I can see it. And now I'm going to exec into the running container, again, scheduled directly on this host. And from there, I'm going to just go ahead and well, that was actually supposed to remove the flag, but I guess I typoed my demo. You know, demo gods, what can you do? But yeah, I mean, you have full access to the underlying file system at that point, right? Because I've just mounted in the Etsy directory from the underlying node into the container as host Etsy. And so I have that full access. The thing that's important to remember about Docker, your big takeaway on Docker, is that when you run the Docker command, contextually, it's being run on the underlying node, which means that if you express Docker up to a container, you're letting that container do anything to the underlying node, anything at all.
Kernel's all the way up. So takeaways, Docker, very powerful for everybody, and perhaps not the most secure option. When used this way, Docker's an unauthenticated API with full access to the kernel. We don't want full access to the kernel, right? I think we do. And how can you mitigate that?
We can restrict the use of host path with admission control, and we'll show that here in a minute.
So you may notice that that was all Docker. Besides host path, which we were using in a Kubernetes manifest, that was a container attack that could work entirely separately from a Kubernetes context. It's important to remember that Kubernetes is a container orchestrator. Basically, containers are what's happening in there, and so container attacks will still work. And then further, it's important to remember that containers are made of Linux primitives. And if you understand Linux primitives and how to attack Linux, you understand how to attack containers. Containers aren't magic, they're just made of Linux. And so if we understand how Linux works well under the hood, we can have really interesting possibilities about how to attack container technology, and by extension, Kubernetes. So let's talk a little bit about container parts. What is a container?
So container is a single process on a shared host. And the thing that's interesting, the way that I think about containers, when I was really kind of getting into like what they actually do, is that if you look at every Linux process or any process in a Linux kernel, you can see that it actually is associated with a set of these namespaces. That's every process on the system, all of them, right? The difference between every process and a containerized process is that those namespaces are mapped to a specific one, specific to that set of processes. So containerization in a way it's just a way of actually providing isolation to the Linux process itself.
But also that means that issues regarding Linux and the way that it maps things like processes, C groups and namespaces can also be applicable to attacking containers in that context. If you can, attack, for example, the way that it deals with C groups and namespaces, you can potentially be able to break that isolation. The way that Linux treats the file system is that all processes, namespaces, all of those things, everything is a file. So can we maybe do something interesting with that file system? We'll find out in a sec. Basically, these primitives, they aren't new. It's not magic. They seem like they're simple and magical and automated, but on the back end, it's the same old attack surface. And we can still do things that apply to that attack surface. Capabilities, system calls, ways that you can manipulate those totally still apply. And the fact that a container shares resources with the host, other containers, and everything else on there means that the attack surface is very wide because it's shared. So if you can compromise the kernel in a container, you then can compromise the kernel on the underlying node. It works like that. And as an attacker, that's really exciting to me because I have so many options. There's so many moving parts in different places that I can go to. And I don't know, I think it's fun. So let's figure out, first let's look at a diagram about that and we'll talk through that real quick and then we'll attack it.
So these containers that we talked about before effectively are just collections of all of these individual pieces, right? So a container might span all of the different C groups or namespaces that are associated with that container. And that represents sort of the packaging of that container at runtime. When we think about an image of a container that's being shipped around, it's really just a tarball. It's just a tarball that represents the actual file system underneath. But everything at runtime just looks exactly like this.
I know that as an attacker, I really leveled up when I started to understand better like the ways that different kinds of attacks against the Linux kernel and user land can apply in this context, the ways that those interact with each other in a container context and outside of it, and the way that those interact. Being able to have a deep understanding of the system really does help in being able to attack it as well as being able to operate it. So here's an interesting thing we might be able to do. Here's a tweet from Duffy a little while ago when we were first working on this talk.
So this is a tweet I put up after seeing another example of this. I thought it was actually pretty smart. What's actually happening here is that we're using kubectl to run a container based on the Alpine image, and we're using NSEnter inside of that container to enter the mount namespace of the first process on the underlying node. And we're doing that because you can see in the specification it says host PID true. That means that when I started this container, I gave it access to the entire PID namespace of the underlying host. But you'll also notice that I'm not giving away like host path or any of that stuff, just host PID, and I'm giving it a privileged context, which is also super powerful. Let's play with it.
Yeah, let's take a look.
So first I want to show you the manifest that's actually going to be doing this. I'm going to deploy it as a manifest, and it describes the same way as actually in the tweet, right? I have my NSEnter command. I'm telling it what mount file system to actually mount into, and then I'm running a command inside of that mounted file system, bin sleep for 99 days. I'm going to use the standard, bog standard Alpine 3.7 image for this, and I have my host PID set to true and privilege set to true as well. Let's go ahead and apply this manifest. And this is the help for NSEnter, and I kind of wanted to just point it out that what's really an interesting thing, this is an incredible tool. NSEnter lets us enter into any of the parts of a container, right? We're talking about a container being a sum of all of its parts. The mount namespace, the PID namespace, the network namespace, all of those individual pieces. The container is just a collection of all of those bits. NSEnter lets me enter into any particular part of one. So I've used NSEnter in my work to actually kind of solve the mystery of how a thing is actually configured. In this example, I'm going to grab a PID of a running Nginx process on a particular host. So I'm going to exec into my container where it's been scheduled and take a look for Nginx PIDs. And I can see that I have a few running. I'm just going to grab that PID ID or the process ID, and I'm going to enter into the network namespace of that process ID. Now, the neat thing about NSEnter is that literally I just have to tell it the target PID, -T, and then the PID ID, and then which namespace or which part of the container I want to jump into. In this case, it's the networking one. And I can see, in my case, that this particular Nginx instance is bound on port 80, and that's what I was trying to figure out, right? I was expecting to be bound on 443, which is why it was not working for me. You can also do things like mount into the namespace, the mount namespace, and take a look at configuration files and that sort of stuff. This all works because every process has a proc/process ID NS directory, and that actually describes the map for that particular process. And this is what we were referring to before. So if I look at the process tree for this one, I can see that this running inside of a container, these are the maps for the C group, IPC, mount names, network, PID, and user and UTS namespaces. These are mapped to these specific namespaces. If I SSH'd in, I would see that they'd be mapped to a different set of namespaces, which are actually identified as the default set for that the Linux kernel is going to use for that user land. But if you're looking for a way to visualize what a container is, this is it. This is what makes up a container, this LS directory right here.
I want to emphasize how incredibly powerful it is to be able to interact with the different parts of the container without necessarily having to exec into a shell. Because let me tell you that as a pen tester, there is no better way to make my day really annoying than to create a container that has no shell in it. Really annoying. And if you can't interact with that, this means that you still can. And if you can interact with all of the different individual, namespaces and all of these things, there's so much control that you can have over it. It's pretty sweet. But what else could we do? Could we do anything perhaps to the underlying node? Could we escalate privileges, gain any kind of control? I don't know, let's find out. So we're not even using host path here. but we can still take over the underlying node of it.
So again, because I have an center and I have access to that host PID namespace, I can just attach to all of the namespaces that make up that particular process and run a bash shell. And so I'm picking PID1 because it's the init system, it's always going to be there, and I'm running bash. And so at this point, I have root on the actual underlying host. And a center is incredibly powerful.
Stop.
Sorry.
Okay, so some takeaways we can take from this. Center is pretty amazing, both for operators and for attackers. Host path is not the only kind of thing that you need to watch out for. You should also restrict the use of host PID if you're trying to harden your own containers. And you should restrict the use of privileged containers because it just makes my life way too easy.
Yeah, one other part of that is that privileged containers actually have a very escalated privilege. You can do anything with any part of the container. You can create new containers. You can do all of that stuff with privileged access. So when you do docker run -- privilege, it's super scary. There's another one where you can actually limit Linux capabilities like sysadmin, but that one is actually still pretty risky, although it still only provides like read-only access to all of those things.
There are really fun container escapes that involve the sysadmin capability though, so
Yep.
That's a thing to keep an eye out for.
Cool.
So is there any way that we can like mitigate against attacks like this or anything like that?
Yes, we can.
Mostly.
Admission control is really like the only defensible space within Kubernetes. And what that does is it represents an implementation at the API server, just as we discussed when we were talking about all of the components. Admission control gives us the ability to validate or mutate objects and determine whether or not we will allow them in. This is beyond authorization and authentication. This is about now that we've seen the manifest, we've gotten past all of those things. Is that manifest requesting access to host PID or host path or any of those things? Now there is a first class implementation of that within Kubernetes right now that's called pod security policies, and we can show you that.
So as an attacker, a couple of things to note here. One, this is actually fairly rare in the wild. Despite the fact that it's the most powerful way that you can harden a Kubernetes cluster, many people don't use it, maybe more commonly than not in a lot of cases. Because the UX is really hard, people don't like it, it's sort of difficult, and people have a hard time with it. That doesn't mean that they shouldn't try, because it makes, by default, if you don't put admission control on it, all of these attacks are just viable. And great for me, bad for perhaps the people who are trying to operate them or defend them. The other thing I wanted to note as an attacker is mutating admission control is really interesting. If anyone is familiar with LD preload and how that can work in a Linux context, LD preload is very useful for both sysadmins and for attackers because it allows you to turn things into other things. And if you have the ability to make any call into any other call, or for example, just dictate that this is going to be your UID or your GID, there's all kinds of interesting possibilities there. We don't really have time to cover them all, and I wish we did, and maybe that's a future talk because it's really awesome, but worth looking into. So anyway, pod security policies. Let's take a look. Can we demonstrate one of those?
One thing I do want to say is that when we were talking about like mutating objects, if we think about it, we've already shown an example of that. When we specified the UID and GID of that particular pod in the security context, what was being told, well, we were actually going to mutate that object at runtime to make sure that we're using that username and group ID. But admission control can do that to all of the things. So I could actually use this tool to do something like inject proxy variables if I'm in a highly regulated environment. And I can inject those proxy variables to all of the pods within a given namespace using things like pod preset within Kubernetes.
Or other kinds of environment variables that might be interesting to me as an attacker.
Yeah.
Pod security policies, when I'm implemented well, can make my life as an attacker really hard. Like I'll run all the same attacks that we were running during this talk, and nothing will work, and it will be really frustrating. Let's maybe see that happen. So we're gonna run the same ones again against one with a good pod security policy, but we'll look at the policy first.
So in this cluster, I've actually turned up a couple of different pod security policies, and we can look at them. There's one that's called permissive and the one that's called restrictive. Probably not super imaginative, but you get the idea. This permissive one really does actually just give access to everything. But the neat thing about looking at the output here is that we can see some of the things that we can actually restrict or constrain with pod security policies. So like first class citizen is like whether to allow privilege at all or whether to allow privilege escalation from within a container. All of what capabilities to add, what Linux capabilities to add, or which to drop by default are required to be dropped before the container will be allowed admittance into the cluster. You can also limit the types of volumes and that sort of stuff. So let's go down here to the restricted one, and we can see that some of these fields actually filled out. So in our case, we're going to not allow privileged containers again in the restricted model. We're going to allow any capability, which we probably should not do. We're also going to only allow specific volume types. So config map, downward API. These are all types of volumes that you can use within Kubernetes and attach to your running processes. We're not going to allow host network. We're not going to allow host PID, host IPC. This isn't the most restrictive pod security policy, but you can see kind of the power of what we can do here.
So running the same attacks against this policy, what happens?
So let's go ahead and rerun the attack, the etcd client YAML that we saw. But we're going to run this as a different user that doesn't have access to that permissive policy. Now we get a pretty useful error message back. So if you're a developer or an operator using Kubernetes and you try to and you bounce against a restricted policy like this, it's going to come back with good information telling you that the pod security policy does not allow host network. It does not allow host path. And so it's not just going to say no and walk away. You're actually going to get some feedback from it.
As an attacker, the first time I ran across this error message, though, I did not find it very clear because it was like unable to validate any pod security policy. Well, if it doesn't have a pod security policy, what's your problem? And it actually means that there is a pod security policy and that it isn't allowing you, which is not, to me, very clearly worded.
So this one also is denied, right? The Docker and Docker demonstration that we provided is also denied, but in this case it's because of host path and also because we didn't specify a seccomp profile. Now, even though we have a restrictive pod security policy in place, it doesn't mean that you can't do anything. Sometimes it may feel that way as a user, and that's part of the user experience kind of problem with pod security policies today. I'm making this look really simple, but it's actually relatively complex in figuring out how the user experience works. But get involved if you're curious about it.
It makes illegitimate use cases harder. It doesn't necessarily do that to legit use cases.
So in our case, I was just going to redeploy that Nginx deployment again, using that user that doesn't have access to the permissive, and I can do things like scale and create deployments, and all of that stuff continues to work. I can see those pods running.
Yeah. So I'm not going to do an attack demo here because it actually was just me being sad. So put pod security policies on your clusters. It can help keep people like me out. So takeaways there. Pod security policies give you a lot of control over what you're allowed to do in a pod and what you're not allowing others to do in your pod.
It's hard to adopt, as I said. It's difficult to adopt mainly because of the way that you associate pod security policies with users or controllers. There's a lot of really great media, including on the TGIKIO website, to talk about how that works.
So does admission control fix everything?
Not quite. There's actually a static pod mechanism, and static pods are manifests that sit on disk near the kubelet agent itself. And the kubelet is actually interesting. The static pod mechanism is interesting because it's generally used for things like bootstrapping the cluster itself. But that static pod manifest that sits on disk will be entirely governed by the kubelet. So even if the kubelet never talks to an API server, it will bring up the pods defined in those files. And it will run them and make sure that they continue to stay running, and it won't ever. It's not susceptible to admission control at all.
It's not susceptible to admission control at all because it's the highest priority. It executes before admission control even applies, and because it's designed to be continually self-healing, that also means that as an attacker, maybe I could do something like persistence that actually doesn't get affected by admission control. I can put my evil pod up there, it'll work. Admission control will never complain, and it will keep coming up when things get spun down. And if you think about it like direct scheduling that we saw from the beginning, can you direct schedule a static pod and completely bypass the scheduler and controller manager?
If you have host paths without admission control, you absolutely can.
So that seems like a pretty powerful attack tool if I can put something there that's going to be persistent, going to bypass things that are trying to prevent me from doing that and are going to bypass admission control too.
Yep. And then the highest priority, as you said. So if you put a manifest down on disk, it will actually make room for that manifest. If there's pods already on the node, it'll kick them out to make room for that static pod manifest.
Fascinating. Is there any way to stop that?
So again, this is going back to the term default. So kubelet by default doesn't have that directory defined, which means that there's no way to actually exploit this by default with the kubelet. However, in kubeadm, for example, the default that kubeadm uses for all nodes is actually to associate a directory with that. So if you know what that directory is, you can place manifest there and away you go.
So it doesn't fix everything, but it helps. So coming full circle, we're really not trying to scare you here. It isn't that Kubernetes is like large and complex and impossible, although it is certainly very large and complex. It's powerful. It allows you to do a lot. And as well as being able to allow you to do a lot at scale, it allows you to make a lot of mistakes at scale. Misconfigurations and not putting admission control on, assuming that Kubernetes is secure by default and developing as such, just means that it's easier for me as an attacker to be able to exploit it. So it's big, it's complex, but it is actually possible, for the most part, to be able to secure it. It's possible to secure your clusters via admission control, and it's possible to work to make the Kubernetes project itself more secure.
That's right.
So how can we do that?
You can get involved. Kubernetes is an open source project, and there are a lot of people who are involved in just working in different special interest groups or groups with focus on particular areas. I put a link in here for, we'll talk about that.
Okay, so Kubernetes is a really wonderful, friendly, welcoming community that is really good to its contributors and tends to be very full of happy developers who don't think like security people. I think some of its design decisions could perhaps, you could think about it in that light. And what that also means is that Kubernetes really needs to have contributors who can think like attackers. It really helps a lot because people are open to it, but they don't necessarily know how to do that. So we want to encourage security-minded folks to come get involved in that open source project. If you do research on Kubernetes, there is vulnerability disclosure info linked on the slide. A bug bounty program, I think, is coming down the pike eventually. And this week, like yesterday, the day before, there was a third-party code audit, and there were a lot of interesting findings coming out of there that are most certainly worth reading that are also linked on this slide.
I just realized there's a typo on that slide, though. If you do want to see the KH audit, which is that third-party, the result of that audit, it's KH-audit, not KH-audit. So
we'll fix that.
Yeah.
And yeah, come get involved and get in touch with us. I'm on Kubernetes Slack as Coldwater.
I'm as Maui Lion.
And yeah, we'd love to help. So to sum up, here are the Black Hat sound bites, the takeaways that we want you to have from this. Check your assumptions. Kubernetes is not secure by default.
Kubernetes is a complex system with lots of moving parts, and it's going to take some configuration to actually get that thing up and running. Go ahead.
But understanding well how the system works on a deep level can help you both as an operator and as an attacker.
Yep.
And it is possible to make Kubernetes more secure, but you do have to put in that work. So put admission control on your clusters, come get involved in the project with us.
And then we have our resources up in the resources link. So if you want to see how I went about doing the demos or explore any of that stuff, you can visit that URL for more information.
We want to thank all of you for coming. This has been amazing. And yeah, thank you very much.
Thank you.